go. Bismillahirrahmanirrahim. In previous class, we talked about steady state problem in rectangular plate, right? Okay, let me just cannot open menu. So we have some rectangular plate with a size B, and I think it was a B and C. So B and C, so we have equation UXX plus UYY is equal 0. U is a function of X and Y. It's unknown function, steady state temperature. So because of the shape of this plate has 4 boundaries, then we have 4 boundary conditions. U0 if it says x-axis, right? If this is y-axis, right? Then U0y is equal, we said like this F1y, UBy is equal F2y, X0 is equal F3x, right? And XC is equal F4x. So means sheet is given here as F4. It's given as F2y, right? It's F3x, and it's F1x. So we call the F1y. So this problem we call as first boundary value problem, right? First boundary value problem. So we split this problem into 4 problems, with 3 homogeneous boundary conditions, and then we can solve this problem using Fourier series. It's done. Today's topic is actually second boundary value problem. So what is the second boundary value problem? We will also consider the same thing. If you have all 4 boundary conditions are non-zero, then we can split into 4 problems with 3 zero boundary conditions. So we will consider 3 zero boundary conditions. 3 zero boundary. Because if it is not 0, then we can split into 4 problems and bring it into 3 boundary zero conditions. Okay, 3 zero boundary conditions. So, for example, problem can be like this. So let's say the same BC. Let's say this site is heat isolated. Let me draw like this: heat isolated. Oh, okay, heat isolated here. How we can express this boundary condition? This boundary condition will be no heat flow from this boundary, right? Heat isolated means no heat flow from this boundary. What does it mean, heat flow? Heat flow is a change of function, no change of function, right? Change of function means derivative. So this direction, what is this direction? It's a y direction, right? So it means uy x0 is equal 0, if you write like this, okay? If you have a heat flow through, let's say, through this boundary, heat is going there and going there, given flow, heat flow. Then if you have a heat flow like this, maybe inside, maybe outside, this is heat flow is given. Then condition you can write like this: ux, because heat flow by x-axis, right? ux by is equal f 4y, sorry, f2y, right? So f2y means heat flow is given, right? So when you have 0, no heat flow. Okay? And condition may be very, very different. For example, you have here just u. Maybe you have just u. For example, here you have just u. X C is equal F3 X, right? So, and also you have here, for example, F1Y function sheet is given F1Y. So then you can write boundary conditions like this. So all boundary conditions are written here. And also, for example, another example is this is our plate, let be BC. So for example, sheet isolated here, it isolated here, here just given sheet. It's still third boundary value problem, right? This condition will be ux by y is equal 0. This will be uy x0 is equal 0. Right? This condition will be u ux 0y is equal 0. So this condition, right? Yeah. So if boundary conditions contains derivatives, then it is a second boundary value problem. Let's solve the following problem. Let's start solution with the following problem. Let's say we will start with the following problem. So let's say we have here sheet u0y is equal f1 0. Let's say 3 problems, right? 0. Okay, let's say we have here sheet flow, no heat flow. Let's say let me use ux, right? Ux, no, this is ux, right? ux b y is equal 0. Okay. Let's say we have here just also sheet flow, no sheet flow here. Uy x0 is equal 0. Let's say you have here u x c is equal given function fx. Let's consider this problem. So if we formulate this problem equation is the same equation, steady state equation, right? Then we have 4 boundary conditions. u0y is equal 0, and ux by is equal 0, and y x0 is equal 0, and xc is equal fx. So we have a second boundary value problem and 3 zero boundary conditions, right? And with respect to x, we have 2. So we will look at this. So these boundary conditions are determining for us eigenvalues and eigenfunctions. Determining for us eigenvalues and eigenfunctions. Not this, right? So it means when you have equation, when we split equation, x double prime, you remember this equation, x double prime over x plus y double prime over y is equal to 0. The question was which one we will shift to the right side with minus. So when you look at here, when you have zero conditions, two zero conditions with respect to x, we leave x, we will shift y. We will leave x and we will shift y. Then will be x double prime over x equal minus y double prime over y. If you have in boundary condition two zero conditions with respect to y, not x, right? Which one? It's all with respect to x, okay. If you have here non-zero condition with respect to x, but with respect to y, you have two zeros, then you will shift x, not y. Then we will have equations, x double prime plus lambda x. So we say this is the lambda minus lambda. X is equal to 0. It's equation 2, 1. Lecture number 1. And for y, we have different. We have here minus y, minus lambda is equal to 0. So from boundary conditions, these two boundary conditions, what we find, if we look these two boundary, x0 and xb must be 0. No, x prime b, right? X prime b and x0 will be 0. So if you look from boundary condition, we find that x0 is equal to 0 and x prime b is equal to 0. So this is Sturm-Liouville problem, and we know the solution from lecture number 2. Right? So what will be lambda n will be equal to n minus 1 over 2b pi square. N is equal 1, 2, 3, etc. And xn functions will be sine 2n minus 1 over 2b pi x. Okay, pi x. So this is a xn. Then, because we already find lambda, we can write here lambda minus 2n minus 1 over 2b pi square times y is equal to 0. And this is strictly positive, so it means with this minus, it is a negative, right? So if I add like this, so all this to get a negative, and then using lecture number 1, equation 1.8, here admission, they're asking admission. Okay, from lecture number 1, for equation 1.8, so solution y will be y, so I must say n, because we have many lambdas, lambda depend on n, and solution also will depend on n, equal an times cosine 2n minus 1, not hyperbolic, right? Hyperbolic, because minus, right? Minus. Hyperbolic cosine, okay, hyperbolic cosine 2n minus 1 over 2b times pi x, right, pi x, okay, plus bn times sine hyperbolic 2n minus 1 over 2b pi x. So this will be solution of this equation 1.8. Where an and pn are arbitrarily constant. We find this from lecture number 1. Now I have many functions. Let me call it un xy, which is a product of these two. So let me write y first. Cosine hyperbolic 2n minus 1 over 2b pi x, right? Plus bn sine hyperbolic 2n minus 1 over 2b pi x, okay, times sine 2n minus 1 over 2b, sorry, not x, y is a function of y. Why you're not correcting me? Y is a function of y, right? It's not x. Y is a function of y. Let me just correct. Y is a function of y. Pi y. Pi y. Y. And here we have pi x. Okay, somebody asking a machine. Okay. Okay, let me. So what we can say about these functions, we can say, again, admission. Okay. All of them, satisfying equation and plus two zero boundary conditions, right? Zero boundary conditions respect to x. So y we have also one more boundary condition. Respect to y we have one more boundary condition, right? Uy is equal to 0. For that I needed to find uy. So if I find d dy un, which is uy, right? So what is this? If you find the derivative, let me admit, asking admission, and down. So what is the derivative? This is an 2n minus 1, 2n minus 1 over 2b pi derivative, right? Pi cosine, not cosine, sine 2n plus 1 over 2by dy pi y, right? Plus bn, derivative of sine is 2n minus 1 over 2b pi. This is from derivative is hyperbolic sine, derivative is cosine hyperbolic, 2n minus 1 over 2b pi y. Okay? So times sine 2n minus 1 over 2b pi x. So we have a condition. What is the condition? Last zero condition, last zero boundary condition is like this, uy 0, uy x 0, uy x 0 is equal to 0. Let's check. Yeah, you can see here uy x 0 is equal to 0. Now we can apply this to un. Let me admit two more students coming. We admit. It's still printing. Okay. If I do this for this un, then what will happen? Dy un at point x 0. So what will be? If y is 0, this sine is 0, this cosine is 1, so we will have bn times 2n minus 1 over 2b pi times sine 2n minus 1 over 2b pi x must be equal to 0, right? So what we get from this number is not 0. This is a function, not 0, not just 0 for all x, right? This is not 0. Then bn must be 0. Then bn must be 0. Okay. Now, if I substitute here, I will get new un functions, many functions. Un, right? Un xy, which is equal, now is different, right? So, which is different, an cosine hyperbolic 2n minus 1 over 2b pi y times sine 2n minus 1 over 2b pi x. So we have many functions. Now what we can say, all of them satisfying three, now 3 0 boundary conditions plus equation, right? So now our problem has one more boundary condition which is not 0. Then solution, we will search u as a summation of all this un. All this un means sum n from 1 to infinity an cosine hyperbolic 2n minus 1 over 2b, right? Pi y, okay, sine 2n minus 1 over 2b pi x. So and now we can use last condition. What is the last condition? uxc is equal fx. uxc is equal fx. So we condition uxc, we use last boundary condition, uxc, boundary condition, use boundary condition. uxc is equal sum n from 1 to infinity an times cosine 2n minus 1 over 2b pi c. Now y is a c times sine 2n minus 1 over 2bx is equal fx, right? So this is Fourier series, this is coefficients, this is the numbers, this is the number, cosine hyperbolic. This is a number. So this number must be Fourier coefficients of f, right? Fourier coefficient of f. So an times cosine hyperbolic 2n minus 1 over 2b pi c must be equal Fourier coefficients 2 over b integral from 0 to b fx sine 2n minus 1 over 2b pi x, right? It's pi actually, pi. Maybe above also. No. Over 2b pi x dx. So from this we can find the formula for A coefficients. A coefficients are equal to over b cosine hyperbolic 2n minus 1 over 2b pi c. Okay, integral from 0 to b fx sine 2n minus 1 over 2b pi x dx. So this is a formula for A coefficients. Then you can substitute A coefficients here. This is a solution. This is solution, and we have a formula for A coefficients. Any questions?
No, sir.
Okay, no questions. So you can solve the same thing in the same way, different other problems. You just changing boundary conditions, then you will have different problems. Okay, let's say another problem. Next problem be like this. Okay, let's see some exercise maybe like this.
Sir.
Yeah.
So if the question asks us to solve the question, we have to do the split equation first.
Yeah, please. Can you speak louder? I cannot hear you.
If the question asks us to solve this question, are we have to do the split equation first? The first step that you mentioned.
I didn't catch what you're asking. Just what is your question?
Are we supposed to do the split equation in this equation?
Your microphone has a problem because your letters is coming different way. So you you want to ask me just you will do the same thing for the solution of the questions? What is your question? I understand. Can you write it? Okay, write from WhatsApp. Maybe I can, because your microphone is changing your voice. Please just write from WhatsApp your question. Did you send WhatsApp or no?
He typed in the chat box.
Google Meet.
Yeah, Google Meet.
Okay. Okay. Are we supposed to do the split equation first to solve this question, or just using the formula that we got? Okay. You see, formula is changing depending on boundary conditions. I will show you another one. You will see. If you can understand what will be solution, what will be shape of solution, no problem. Because for this plate, possible boundary conditions, how many will be? Many, many. You see, many, many. I cannot bring all as in one formula, but concept, idea is the same. Concept and idea is the same. So, first of all, when you see problem, eigenvalues and eigenfunctions define it from 2 zero boundary conditions, right? 2 zero boundary conditions. Okay, let's just maybe first admit someone is asking me. Okay, admit. So, depending on boundary conditions, right? Whatever boundary condition, if you have here 0, 0, 0, 0, let me just make some general remarks, maybe it will be clear for you. If you have 0, 0, then you have lambda n, whatever, derivative or whatever, right? I'm not just say it's first or second, not classified. Boundary condition like this, 0 here, 0 here. Then you will find lambda n, you will find xn, right? xn will be either cosine or sine, usual, right? Then y will be hyperbolic. Okay? If you write solution, or if you write un first, un, right? Okay, un. If you write un, your un will be like this. An cosine root of lambda, cosine hyperbolic, root of lambda n times y plus bn sine hyperbolic root of lambda n y, right? Times eigenfunction xn, whatever xn. Okay, this is some more general one. So if you have zero condition with respect to x, then you will find lambda n and xn. Then un will be functions with satisfying equation and 2 zero boundary conditions. So you don't need it. If you know this, you don't need it to split equation and so on. You just start from this point, no problem. But must be careful because you can make a mistake. So then using boundary condition here, using this boundary condition, you can find that an equals 0 or bn equals 0. Okay? It depends on this boundary condition. Depends you have derivative or you don't have derivative. Right? We have derivative, that's for bn 0. If no derivative here on this additional third 0 boundary condition, then an will be 0. Remember, if you have no derivative, then an will be 0. If here you have derivative, then bn will be 0. Then you will simplify your function u. Clear? Now, if you have this thing, let's say, you have 0, 0, whatever, derivative or no derivative, right? And what will happen? Then you will find lambda n and you will find yn, where the yn will be either sine or cosine, right? Usual sine and cosine. Then you will find xn as a combination of hyperbolics, the same, but the shape is the same, an cosine root of lambda n, sorry, cosine hyperbolic. Cosine hyperbolic root of lambda n x, root of lambda n x, you see, plus bn sine hyperbolic root of lambda n x. So then xn will be, then you will continue the same way with un, and you see, if you have two zero conditions with respect to x, then you will find xn and lambda n, then y will be hyperbolic. This is y in the bracket, right? So if you have zero conditions here, for example, here fx, right? So then you will have un as this one, an cosine root of lambda n x plus cosine hyperbolic, sorry. Then bn sine hyperbolic root of lambda n x, yn y. So this will be shaped. This function is satisfying two zero conditions, right? Then you will use third one, this zero condition, and find from this you will find that an 0 or bn 0. It depends on your boundary condition here. If you have no derivative, then an will be 0. If yes, then bn will be 0. Because cosine hyperbolic and sine hyperbolic, right? This is a scheme. Did you get the answer?
Yes, sir.
Okay. Okay. So let's see one exercise. Maybe we will get one exercise. Let's say this is our plate, BC, size BC. Okay, let's say a problem like this, uxx plus uyy is equal to 0, ux, u0x, sorry, u0y is equal to 0. Let me put here derivative, so it means this side is heat isolated. So ux, let me say ux by is equal, let's say 3 sine let's say 3 sine 7 pi y over 2. Let's see. 3 sine 7 y over 2 minus 5 sine 11 y over 2. Let's say like this. And so means here you given function, right? Or heat flow is given. Here is heat flow is given, like this. So let's say condition when y equals 0, let it be 0. So we have here 0. Okay? And we have a condition uy xc is equal 0. So what means this condition? This side is isolated. So what we have? we have here we have a 0, always 0, 0 on this boundary. Two boundaries are heat isolated, and here we have a heat flow. Heat flow is equals 3, 7 sine 7 y over 2. Okay, let me just choose B as pi. So B, let be pi. Let's see B equal some number. I just want to be some numbers. Let's say C equal 2, for example. So 2. Okay, this is problem about this. Now I see here 2 zero conditions. This 2 zero conditions, 2 zero boundary conditions. They are with respect to y, not x. So what we find from this, we find lambda n equal, what will be lambda n? Oh, no, not like this. Yeah, let me say this is pi, this is maybe some different number. Yeah, this is different number. No problem. Let's choose this be pi, C pi. Let's say C is pi. Okay. And B, let B just simply say 2 pi, for example. 2 pi. Okay, 2 pi. So what will be lambda n? Lambda n we find from these conditions, right? From 2, 0, with respect to y. Pi. So you have on left side, you have no derivative. So from lecture number 2, I refer the table. I see on left side, we don't have derivative. On right side, we have a derivative. Then what will be lambda n? Lambda n will be 2n minus 1 over 2. What is the length? Length is equal to pi times pi square, right? This is a formula in lecture number 2. So pi and pi will be cancelling, right? So actually, then I can write without pi, because pi is cancelling. I can write it like this. Square. This will be lambda n. Clear? So what will be yn? Yn y is equal, it will be sine. When you have derivative on left side, right side, left side no derivative, it will be sine. Sine 2n minus 1 power 2y. This will be eigenvalues, this will be eigenfunctions. Because when you split, I will write here, when you split, you will get this problem with respect to y. Because now y will be with plus, right? Y double prime plus lambda y is equal 0. Y0 is equal 0. Y prime at pi is equal 0. So this is the solution. Okay? So without splitting, you can write. If you can, it's good. From boundary condition immediately. So then what will be x? Okay? For x, you will have here minus lambda. That's the difference. Then for x, I have a solution. Xn is equal an cosine hyperbolic 2n minus 1 over 2x. Clear? Plus bn sine hyperbolic 2n minus 1 over 2x. This will be xn. Now I can use, I can write un, for example, at this stage, un, if I say un xy, which is equal xn an cosine 2n minus 1 over 2x plus bn sine hyperbolic 2n minus 1 over 2x times yn is a sine 2n minus 1 over 2y. So we use now all of them satisfying 2 zero boundary conditions, right? Now we use last one. We will use last condition, last zero boundary condition. What is zero boundary condition? This one. ux 0y is equal 0. We want to use ux derivative 0y is equal 0. How to use for un? I need a derivative, so I need a derivative from un, partial derivative with respect to x from un, then I can substitute x equals 0. So what will be the derivative of this? If you find the derivative, so what is the derivative? This cosine hyperbolic h. So it is an times this number is coming after derivative, then cosine hyperbolic, sorry, not x. No x here. Then cosine hyperbolic, not cosine. It will be sine after derivation. Okay. Times sine hyperbolic 2n minus 1 over 2x. Derivative for first term, second term will be bn 2n minus 1 over 2 cosine hyperbolic 2n minus 1 over 2x, right? Times sine 2n minus 1 over 2y. Then you substitute x equals 0. If you see what will be un 0y dx, this condition, right? This condition. So then it is equal. So first term is vanishing because sine hyperbolic 0 is 0. So we have bn 2n minus 1 over 2 times sine 2n minus 1 over 2 y is equal to 0. So we found that bn must be 0. So all bn coefficients 0. So you remember I told you earlier, answering to your question. So what's happening? If this condition has a derivative, then bn 0. If no derivative, then n is 0. We have a case when it has derivative, then that's why bn 0. Then what will be un? Un will be equal an times cosine hyperbolic 2n minus 1 over 2x, right? Sine, usual sine, 2n minus 1 over 2y. So all of them all satisfying equation plus 3 zero boundary conditions. You can verify what I'm writing, you can verify. But I derived from the equation and boundary conditions. They must satisfy. Now, solution we will search in the form of combination of all this un equal sum n from 1 to infinity an cosine hyperbolic 2n minus 1 over 2x sine 2n minus 1 over 2y. So then we use last boundary condition. What is the last boundary condition? Last boundary condition was, what was the last boundary condition? Let's see. Heat flow is given. Derivative at 2 pi equal to this. Heat, I need a derivative, right? So let me write this. Last boundary condition was like this. U x 2 pi y is equal 3 times sine is 7 over 2 y minus, let me see what was the problem, minus 5 11 over 2 minus 5 sine 11 over 2y, right? So we have to use this boundary condition in order to find an coefficients, right? For that, I need the ux first. What is ux? Let me find ux. Ux xy, this is derivative from this, right? This is solution. I need derivative of this. Equal sum n from 1 to infinity an. Derivative is, we have 2n minus 1 over 2 sine hyperbolic 2n minus 1 over 2 x times sine 2n minus 1 over 2 y. Okay? Now I can check this condition. What is ux 2 pi y? Okay, it's equal sum n from 1 to infinity an 2n minus 1 over 2 sine hyperbolic, right? Sine hyperbolic 2n minus 1 pi. When x equal 2 pi, this will cancel with this, okay? Times sine 2n minus 1 over 2y. This should be equal, according to boundary condition, 3 times sine 7 over 2y, right? Minus 5 times sine 11 over 2y. So then these numbers must be this number. Let me just show. These numbers, this is number, right? This is a number. All these numbers must be Fourier coefficients of function which is on the right side. So an 2n minus 1 over 2 sine hyperbolic 2n minus 1 pi must be equal, so 2 over c, right? 2 over c, then 1 over pi. 2 over c, remember formula, 2 over c. C is 2 pi, that's why it will be 1 over pi, integral from 0 to 2 pi, 2 over b, right? 2 over b, 2 over c. With respect to y, 2 over pi, y is a pi, right? Y is a pi, 2 over pi. Y is pi. Let me check. Pi, yes, y is pi. 2 over pi, integral from 0 to pi. One over pi, integral from 0, no, 2 over pi. 2 over pi, from 0 to pi. So function is 3 sine 7 over 2 y minus 5 sine 11 over 2 y dy, no, sine 2n minus 1 over 2 y dy. So what we can say about this integral, because this is eigenfunction, you see sine 7 over 2, 11 over 2, actually sine 7 over 2, 7 you can write like 2, 7 you can write like this, 2 times 3 minus, no, 2 times 4 minus 1. 11 you can write as a 6 times 2 minus 1. So means this will be equal, using orthogonality you can find this equal, you can verify also if you like. It will be equal to 3 if n equals 4. You can just check it. And it will be equal to minus 5 if n equals 6. Okay. And 0 otherwise. In other cases, it's 0. So only two coefficients are not 0. Coefficient number 4, and it's equal to 3, and coefficient number 6 is equal to minus 5. So then I will write this equation for both. So what I have, for example, when n equals 3, what we have? A3 on left side, A3, so what is this? No, n equal 4, right? No, 3. N equal 4. When n equal 4, I have A4 times 7 over 2 is 2n. I'm calculating this 2n minus 1, 7 over 2 times sine hyperbolic 7 over 2 pi, 7 pi over 2 Okay, you see this is 7 pi over not 2, not 2. Okay, not 2. This 7 pi. Okay. 7 pi. Okay. 7 pi. 7 pi. Okay, this is 7 pi. So equal 3, right? When n equal 4. So this, from this I can find A4. What is A4? A4 is equal, what will be 6 over 7 times sine hyperbolic 7 pi. Okay? So when n equal 6, then I have A6 times, see what we have here, 11 over 2 sine hyperbolic, this is 11 pi, this is equal to minus 5. Right? This is equal to minus 5. So this will, from this we find A6. A6 is equal minus 10 over 11 sine hyperbolic 11 pi. So, and an equals 0 if n is not 4 or n is not 6, right? If n is not 4 and 6, n. If I say or, it will be wrong, right? N. If it is not 4 and not 6, then it is 0. So what will happen with my solution? Where is my solution? This is my solution, right? This is a solution. So from infinitesimal, I remain only 2 terms, n equal 4, n equal 6. So I have an cosine and this sine, right? Cosine and sine. Solution now, I can write solution uxy is equal a4, which is a 3, over, so 6 over. Okay. It is 6 over 7 sine hyperbolic 7 pi, right? Times, we have a cosine hyperbolic 7 over 2, 7 over 2x, I think. Let me check again. Yeah, this will be 7 over 2x. 7 over 2x, okay? Then we have usual sine, 7 over 2y. Okay, next term is minus 10, is coefficient, right? A6 coefficient. 11 times sine 11 pi cosine hyperbolic 11 over 2x sine, usual sine, 11 over 2y. So that will be solution. Now let's verify, just verify, is it solution? Maybe we made some miss something, right? Mistakes or miss something in sign or whatever, right? Let's verify. So what we need to verify? We need to verify equation and 4 boundary conditions, right? So let's start with boundary conditions. So what are the boundary conditions? Without problem, okay. For example, I will start with this two, respect to y. When y is equal 0, must be 0. Okay, let me check. Also, I will need a derivative because boundary condition has a derivative, right? So, okay. So I need a derivative with respect to y. What is the derivative with respect to y? Let's find the derivative with respect to y first. What is the derivative with respect to y? We must differentiate sine y, right? Then from derivative, it comes 7/2. If I write here 7/2, it will be 3, right? 7/2 will be 3, 3 over. Now will be 3 over sine hyperbolic 7 pi, okay? Because from derivative with respect to y, I have here 7/2, 7 plus 7, 6 plus 2, right? Then I have cosine hyperbolic 7/2x. This is now cosine. Cosine 7/2y. Clear? So now next term, derivative from sine 11/2y. So when you find the derivative from this 11/2, then it will be minus 5 over sine. This is hyperbolic, right? I forget here h. H, hyperbolic. What about above? H, we have h, okay. Sine hyperbolic 11 pi, okay. Then I have this cosine hyperbolic 11/2 pi, 2x, right? Then this sine became cosine after derivative. I need one more derivative because you see boundary condition. I want to check all boundary conditions. That's why I need the, you see, I need the ux, I need the uy. So both I need, right? Ux and uy. And now I need the ux xy. So if I differentiate now, what will happen if I differentiate this cosine? Cosine, if I differentiate cosine, this will be 7/2 again is coming, right? So this will be 3 sine hyperbolic 7 pi. Its derivative from cosine, I have 7/x, right? Then cosine became sine. Sine hyperbolic 7/2x, right? 7/2x. Then sine 7/2y. Okay, done. So minus now derivative from this. Oh, this is not cosine, this is sine. Why people? Oh, cosine, right? All cosine there. Because B was 0 in our case there. Now derivative of second term with respect to x. I must differentiate this cosine. When you take derivative, 11/2 is coming. 11 will cancel with 11, so I have 5 sine hyperbolic 11 pi. Next will be sine, derivative of cosine, right? Sine hyperbolic 11/2x, right? Then sine 11/2y. So I need all derivatives. Now I can check all conditions. So first of all, what we need is, I will check all 4 now. We can start from this line, it doesn't matter. Ux 0y must be 0. Okay. Ux 0y must be 0. Ux 0y, Ux 0y. So what will be U0y? It will be 0 because sine hyperbolic 0, you see? You have this one. 3 over sine hyperbolic 7 pi times sine hyperbolic 0 when x is 0, right? And sine 7/2y. So this term is 0, 5 over sine 11 pi, right? This again sine hyperbolic 0 because x equals 0. Sine 11/2y equals 0. It's okay, right? So now let's check next condition. What is the next condition? Here's my conditions. Okay, next condition, this one. Derivative at 2 pi. I must check what will happen with derivative at 2 pi. Derivative I have here already, right? So what is the derivative of this at 2 pi y? So it is equal 3 over sine hyperbolic 7 pi. So what will be this if you substitute x equal 2 pi? Sine hyperbolic 7 over 2 times 2 pi. X is 2 pi, right? Now it will be also 7 pi. The same thing as like this, right? Then you have sine 7 over 2y minus 5 over sine 11 pi, right? Then we have sine hyperbolic 11 over 2 times 2 pi will be 11 pi, right? Times sine 11 over 2 y equal. So what will happen with this? So this will cancel with this, will be 3 times sine 7 over 2 y, right? Minus 5 times sine 11 over 2 y. That's also okay, right? And let me just see what will happen if you check next conditions. So next we needed to check ux0, right? ux0. Where's u? U is this one, right? U is this one. If you check ux0, if you say y is 0, what will it be? Sine 0 is also 0, sine 0. Clear? If you want to write, you can write it like this. ux0 is equal, what was the u? U was 6 over 7 sine hyperbolic 7 pi, something like this. Let's check. Okay. Cosine hyperbolic 7 over 2 x sine 0, because I substitute y equals 0, right? The same. 5 over, not 10 over 11 sine 11 pi hyperbolic 11 pi times cosine hyperbolic 11 over 2x 11 over 2x sine 0, so it's equal 0, right? The last is you needed to check uy x pi. This must be 0 according to condition. Let's see. uy x pi must be 0, right? Where's the uy? Uy we have here, uy. This one is uy. You see, this one is uy. You have 3, you have cosine, you have cosine. Let me write this. Just I will substitute y is equal pi, okay? Y is equal pi, and I will copy this. Okay, it's equals 3 over sine hyperbolic 7 pi, so times, what was times cosine? Yes, cosine equals cosine 7 over 2 x, and this was, I think it was a cosine 7 over 2 times pi minus 5 over sine hyperbolic 11 pi times cosine 11 over 2x cosine hyperbolic 11 over 2x. Then I have cosine 11 over 2 pi. So let's check cosine, okay. Then this cosine is 0. Cosine 7 pi over 2 is 0. Yeah, it is 0. Even times of pi over 2. Even times 7 times of pi over 2, cosine 0. 7 times pi over 2. The same. Even odd times, odd, not even. Odd times 11 times pi over 2 is cosine 0. So this will be equal to 0. So what we have done, we verified all conditions, right? So we verified all conditions. Now equation. we verified all boundary conditions. Now equation. Now equation is, for equation I need the uxx and uyy, right? Let me find uxx. Let me find uxx. What is the uxx? It is derivative from ux, right? So this is ux. From ux, if I take derivative, what will come? Let's look at this. If you find more derivative, so this will be 7/2 is coming here, this will be cosine. So cosine in usual sign. Cosine hyperbolic, usual sign. And you have these numbers before this, right? 33 times 7 is 21/2, right? 21/2, okay. So what we have here, 21/2 sine hyperbolic 7 pi, right? Times cosine, right? Because first derivative was sine. Again, let me check. Yeah, sine. Now it's cosine. Cosine hyperbolic. Cosine hyperbolic. This is cosine hyperbolic. Cosine hyperbolic 7/2 x. So this will be sine, usual sine, 7/2 y. Okay, minus, this will be, if you find derivative, 55/2 times sine hyperbolic 11 pi. This will be again cosine hyperbolic 11/2 x. This will be sine 11/2 y. So this is uxx. Now uyy. When you find, how you find uyy? This is second derivative from u with respect to y. So it is first derivative from, so you see, this is uy. If you differentiate this cosine, derivative of this cosine will be minus sine. Derivative of this cosine, again minus sine. You have the same. When you find derivative, 7/2 is coming here, right? But with minus. You see, derivative of this is minus sine. And 7/2, I will multiply to 3. The same, derivative of this is minus sine. And 11/2 is coming. So what will happen? So this will be minus 21/2 times sine 7 pi cosine h 7/2 x sine. Now it is sine 2 y. This will be plus 55/2 sine 11 pi cosine hyperbolic 11/2 x sine 11/2 y. So, and now you can see that when you add plus, so uxx plus uyy will be equal 0. So we found the solution of this equation, which is satisfying given 4 boundary conditions. Any questions? Any questions? Okay, if no questions, let me stop recording. We don't need extra megabytes.